Okay, wow. 100%. 굉장히 드문 케이스다. 가자. 야. 안 보자꾸나. 트리플 번. 앞에서 맞췄는데 이걸 맞추게 됐어. 어우 씨, 부럽단데. 오케이, 와우, 오늘 왜 이래? 왜 그래? If there's a triple and double bond together, double bond has a higher probability. 요새 좀 정신을 차리는구나. Okay, this is a good catalyst. If you use this catalyst, then it keep going to the arcane. Okay? So to stop it, you need to do something in the middle. Okay, with the lateral catalyst, addition happens on the same direction, chain addition. That's why cis product. Transfer one by one, then it gives you a more stable trans alkane. Markovnikov, hydroxyl added not the end, it's the inside, that's why it forms ketone. Right? Mercury ion is a replacement of a proton. Product is the same, just a milder condition in the laboratory. That's oxynucleation. One hydroxyl rearrangement gives the same product, ketone. This is aldehyde. 이게 헷갈리면 우리 구분을 여전히 못하고 있다는 얘기지. 마르코프니코프, 페네타일 마르코프니코프. 이게 우리 배운 전부야. If it was alkene, starting material was alkene, product is alcohol. If starting material was alkyne, in all was intermediate. Rearrange either ketone or aldehyde. Okay, it was 25. The value of alkyne is 25. 아직 들어와 됐을까도 안 되려면. Okay, this pKa is 35. Do you think that's a left side reaction or right side of the reaction? pKa 1035, which is more acidic. 10 is more acidic. That means most likely common reaction if you add ammonia in the water, this is formed. So that pKa is dissociating this with proton and ammonia. That's a pKa 10. That's a weak acid, but still that's a reasonably tangible acidity. Okay. Here we talk about the 35. This acidity is this one, loose proton, and then forming this. What's the name of this? Amide. We use the sodium amide for this. This one is much weaker acid. That's why 35 conjugated base is much stronger base than 25. That's why it can deprotonate from alkyne. Okay? This is alkenes. This is alkanes. So with this, sodium amide cannot deprotonate this. Okay? But it can deprotonate this. It can remove proton. That's why alkyne can become carbanion, nucleophile. Okay? That's what we have learned. Okay? So those were key part we have learned. Oxymercuration or hydrobolation forming aldehyde or ketone, and alkyne can become nucleophile by adding sodium amide. Okay, that was key contents in alkyne chapter. Okay. One more. Okay, perfectly wrong answer. There was two kinds of reactions. Double bond is a nucleophile. 아주 중요한 얘기하고 있어. Double bond is a nucleophile. If there was a Cl2, one possible reaction is 2 electrons is donated to one of those Cl that becomes Cl plus. Catalytically flip, forming bromonium, in this case I don't know, chlororium intermediate, okay, positively charged. Cl minus comes from behind the tag ring open. Anti-addition. There was no radical. This is ionic reaction. You are confused with alkane plus Cl2 and with the light, Cl was decomposed in the middle, Cl radical, and that generates product. Usually there was monoalkyl, monohalomethane kind of product we formed. That was a radical reaction. If this was a radical reaction, there was a possible if you add radical source or if you add light, then it can generate radical too. Then what is your product? Alkene with a radical source, what is the product? Was it alkane? Radical, double bond, react with the radical, give one to this coupled, the other one, make another radical, and it can be react with another at the double bond. What is the product? Polymer. Polymer was the product. Okay. With the alkene, if you generate a radical, the product is a polymer, not this product. That means even similar reactions, you can get two different reactions. Whether you induce radical reaction or you use ionic conditions. Ionic condition usually in protic solvent. Protic solvent means which has a proton source, water or alcohol, because they can stabilize the ion intermediate. Okay? So you need to distinguish these two reactions, reaction paths. to check whether you really understood that. Ionic reaction, the breaking was Cl plus and Cl minus. That is a heterolytic cleavage, right? Bond dissociation energy, maybe I told you 3 times at least. Bond dissociation energy is breaking in the middle, homolytic cleavage. These are the strengths of a bond. That is related to radical reaction. Okay? Based on this, we move to today's lecture of, oh, don't. 지금인데 하나 주고 있어요. 힘내서 오늘 열심히 해보자. 아마이도 맞췄습니다. 힘내서 가지고. Oh shit. 큰일 났네. 다시. 쫓고 안 하네. 아이씨, 망했네. 어떡하지? 오늘 슬라이드 없이 해볼까? 좀 해볼까? Today's topic is alkyl halide. 자, 이번 주하고 다음 주에 배우는 이 2주 동안 배우는 내용이 여러분들이 배울 유기화학의 가장 핵심을 다루고 있습니다. 이 2주를 잘 소화하면 여러분들이 볼 모든 유기화학 시험의 70%는 배운 것 같아요. 앞에서 이제 원행을 했고, 지금부터 배우는 이번 주와 다음 주에 배우는 이 2개 주에 배우는 내용이 이것만 잘 마스터하면 절반 이상 배우는 거예요. 1, 2학기를 통틀어서. 여러분들이 왜 내 반을 선택해서 이 반에 왔는지 모르지만 여러분들은 굉장히 행운이라고 생각해야 된다고 봐. 내가 어떻게 하면 여러분들한테 이 교육을 최대한 쉽고 잘 들어갈 수 있게 가르칠까 밤낮으로 노력하면서 이 수업을 구성하거든요. 한 번에 듣고 잘 되는 경우는 잘 없기는 해. 그래서 내가 계속 반복하지. 그게 느슨한 마음으로 들으면 잘 안 들어가. 교육이 가장 잘 될 때는 배우는 사람이 파르소 때처럼 받아들일 준비를 하고 받아야 들어가. 자, 다른 차처럼 몰라도 요 2주간은 최대한 집중해서 같이 생각하고 한번 해봐. 이 안에 유기화학이 다루는 거의 모든 내용이 다 들어있어. 오케이? 지금 파일이 안 되는데 저 파일 어떻게 가져갈까? 내가 가서 가져와야 되긴 하는데, 자, 해서 문제를 주고 가볼게. So the topic, the object of this week, main player is alkyl halide. This week and next week. Okay. Now we are going to play with this molecule and look at this molecule and think about its property and how it can work. And here, if I give you nucleophile together here, and what will I give you further? Okay, let's think about reaction with the nucleophile first. Look at this molecule and try to understand. 한번 느껴봐. 이 분자가 어떻게 생겨보고 있을지, 어떤 프로퍼티를 갖고 있을지. 내가 준 단어들은 homolytic, heterolytic, electron poor, electron rich. 계속 이런 얘기를 계속 반복해 왔어. 이 얘기들이 한꺼번에 마음에 안 와닿더라도 지금부터 생각하고 2주간 같이 생각해보면 이게 꽤 친해질 거야. 그러면 아주 처음 보는 문자를 봐도 그 느낌이 살아올 수 있어. 지금은 단 3분 정도 빨리 갔다 올 테니까 그 문자를 보면서 누가 한 사람 나와서 이제 1분자 가지고 지금 얘기할 거야. 누가 나올 건지 발언티어 할 준비하고 있어. 누가 나와서 이 분자를 가지고 한번 분석을 해볼래? 10%한 분자를 가지고. 또 수주가 아니구나. 그러면 오늘 좀 넘기는 유찬이가 해볼까? 유찬아, 문자 쓰고 있어도 다 보여. 빨리 나와, 시간 없어.
어떤 분석을
Chemistry is the object of molecule. Among molecule, what do we handle? What component do we look at? 화학은 뭘 다루는 학문이야? 도와줘. 화학은 뭘 다루는 학문이야? 전자를 다루는 학문이네. 전자 분포가 어떻게 되어 있을까? 됐어, 수고했어. chemistry, especially in chemical reactions, reaction means change. The change is change of a bond. One bond is composed of how many electrons? 2 electrons. The bond is changing. 2 electron movement happens. Right? Now, in the case, rather than this lone pair electron structure, the most important thing is the bond is where is the main density of electron in the molecule. Electronegativity, CNH, 2.5, 2.1, electron is a little shifted to the carbon side. That's why we count this relationship, carbon is -1, this is +1. With the accretion number of formal charge. It's a accretion number. Okay? So electron is a little shifted to this direction. Now between these two, this one still the difference is not very much. So slightly shifted to the carbon. Now any heteroatom, okay, from carbon to the right side. Nitrogen, oxygen, halogen, everything on this side, electronegativity is higher. More electron withdrawing. Okay? That's why this is correct. Electron is shifted to this side. Means this is electron rich. Relatively. Electron poor. Well, this relationship, 2 electrons make 1 bond. Maximum charge of this is -1. Maximum charge of this is the +1. Okay? That makes 2 electrons make the decision. 2 electrons moved all here, -1. This means less than 1. Still, this is major electron is shifted to this direction. We show that with the color. Bromide direction is the red color or blue color?
Yeah.
It's red color. Carbon, bluish. Carbon is electron poor in this case. That's the picture usually we draw this way. Okay. That feeling, if you look at the molecule, if you can get that feeling, first step is very good. Now, electron direction is, let's say you can draw, that's really this direction, this way. If any electron movement comes in, okay, electron poor species comes in, for example, proton. If a proton comes in, that's acid, and electron poor. If that comes in, where does it bind? You think proton binds to bromide side because that's electron rich. Right? If there is any electron rich species it means, it may bind to where? It's carbon or hydrogen, not bromide side. Right? That's very simple electrostatic interactions. Right? Now the direction of movement, if that is attack carbon side, nucleophile attack carbon side, then direction wise, electron is already shifted on this axis, moved to this direction. Right? The best direction is coming exactly on this trajectory, on the same line, nucleophile using its extra electron. How many electrons? Maximum 2 electrons to make 1 bond. 2 electrons is moving from this side. Always we draw this the arrow electron movement. How many electrons? 2 electrons. Okay, 2 electrons moving. Best direction is on the same line here and attack this position, making new bond. Now for this carbon, it was not very happy, but it had a bond. Now it gets extra bond from behind, then it should choose. I had one partner here. Now another partner comes from behind here, not from the same direction. Okay? Then I should choose whether I let go this partner or repel this partner. If I repel this partner, then no reaction. It's the same product. But if I choose, okay, I get my hydrogens are here. If I get this, then I'm in the middle. In both sides, if I'm interested, then this is a planar structure. It's very similar to carbocation. Okay, carbocation state. It's planar structure. And if I decide to take this bond and let this go, then this goes this way. Stereogenic center configuration is originally here. Is a change it, correct? And then new bond formed. Where? Behind. That is substitution reaction. New coming in is a nucleophile. Nucleophile is defined as electron-rich species. And this group, if it moves out, push this, make a new bond, and then this take these two electrons as a result. Then it becomes a Br minus. It's a maximum charge you can get. In a sense, Br minus is also electron rich. That can be nucleophile too. That means this reaction can be reversal. Now it formed this nucleophile added here, but this Br minus can come exactly the same way, and then this reaction now Br minus comes back, attack, and then go back to the original structure. It's also possible. That's a equilibrium reaction. Okay. So this type of reaction we call substitution reaction. That's S type of reaction. So we are going to learn later different type of reaction, E type of reaction. Anyway, let's think about the S type first. Okay. This is what we are going to see, and this is the main chemistry. Now that's why attacking one we call nucleophile. This one is leading. This is a lead. That's why this group we call leading group. In English, if you call quickly leading group, then that's L-I-V-I-N-G. Leading here, okay? That should be a little longer. Leading group. Okay? So nucleophile is coming in, and leaving group moves out. That's something you needed to have in your mind. Okay, that's substitution as a reaction. Okay? So keeping in mind, now any kind of alkyl halide can be good electrophilic material because the carbon is delta plus. Okay? Now, we start a little of those naming. It's simple. Not very difficult. Now, alkane, 7-alkane, methyl, bromo, and lower number. Bromo is one of those substituents. Just the alphabet is B, but anyway, giving those two. Start 2, then 2-methyl, 1-bromo. Okay. Dimethyl, bromo. And position, alphabetically are coming first. 5-bromo, 2,4-dimethyl. Not difficult. And if it is similar way, it doesn't matter. Anyway, the lower number take those the bromo alkyl at the same the priority you can choose. And if there's a chloro, then that's also similar. Just alphabetically, bromo comes first, B and C, and then methyl. Okay. So naming is not difficult. And in this case, now Br and C, then we choose the lower, the alphabetical order has a lower, the lower number because it goes 1, 2 this way and 1, 2 this way. Then we choose this one and then 2.5 meters. So not difficult. And also we can give alkyl group, methyl iodide, isopropyl chloride, cyclohexyl bromide is also acceptable, or bromo cyclohexane. Okay. Naming wise, we are not going into too much the complicated situation. So based on this, no problem. We just the check. Two types of reaction is possible. One is a radical type of reaction. The other type is ionic reaction. radical type breaking in the middle. Ionic is giving this electron to one side, heterolytic cleavage. Now we learned this. Methane and chlorine. Okay, chloride is a Cl minus, chlorine is a Cl dot or Cl2 neutral, and with the light. And if I remind you, with the light, it tried to find the weakest bond. In this case, the weakest bond was the Cl to Cl. Okay, there was about 50, 60 kilocalorie per mole. Carbon was about 100 kilocalorie per mole. That is a broken first. Cl dot generated. Cl dot captured one hydrogen quickly, and then it generates CH3 radical, and that reacts with the Cl2 and regenerate Cl dot. It make propagation, chain reaction. Okay, that was the radical reaction we have learned. If it is alkene, then alkene does not stop like this. Alkene generates another radical on that molecule. That's why it keeps going. It generates the polymer. Okay, that was a radical reaction. To do radical reaction, you need to have a radical generator. In this case, Cl2 itself is a reagent and also radical generators. In polymerizations, we have seen peroxide, OO molecule. It can be broken and O dot it could generate. In the case, catalyst, the radical was a catalyst. But in this case, Cl2 is participating in the molecule. That's why it's an initiator, but at the same time, that's a reagent. That's why we need to add both of them, methane and chlorine. By the way, this reaction, we just saw only one, but it can go keep going. It does not stop here. Because this one also can react together with the Cl2, and it can add one more chloride and one more, and it can go to the end. So to control these reactions, you need to control the amount of the Cl2. Maybe one equivalent, half equivalent, you can get this. No, sorry, one equivalent, you can get the single chloro. If not, it can keep going. Okay. There is a radical reactions. In organic chemistry, radical reaction, not many, because radical reaction, as you see here, it's difficult to control. Very reactive and keep going, and control is difficult. So radical reaction is usually not very common to see. Now, still, if you see these reactions, so if you look at here and then if you see light, then you should catch or maybe generate the radical. Okay, Cl dot generated, and you may attack. Now, methane case is only one position, so product is only one. But in this case, now you can attack, take a proton from here or hydrogen from here. So you can generate the two products. Product ratio is 30 to 70. Now, this is a primary position, this is a secondary position. Reactivity ratio is what? Which is more reactive, secondary or primary? 30 to 70. This is secondary, right? What is the reactivity ratio? 7/3. 7 divided by 3. 7 나누기 3. Is that the reactivity ratio? If you compare those reactivity ratio, okay, primary is 3 and secondary is 7, then the ratio can be, one way is you can calculate it this way. Then what's this number? 빨리 계산해. 이보다 조금 크네. 2.3 정도 된다. Is that the ratio? Reactivity wise, if you look at those reaction sites, chloride can attack this position and the position 3 proton, totally 6. Secondary position wise, there's only 4 positions. 4, right? 4 positions. Then reaction site is not exactly same between 2, then this number should be calibrated. Right? Then this number should be calibrated, even though it has 6. This ratio. because it is reactivity over 4. This reactivity is 4, 6. Then what's the number of this? 이거 계산 빨리 해볼래? 3.5. Okay. Reactivity between secondary to primary is a little higher than we just have seen, 2.3. 3.5. So means about 3 times, 4 times faster for secondary positions. How about this? Now we are comparing primary versus tertiary. Tertiary looks like a smaller, but if you apply the same rule, primary position 9 position possible. Tertiary position is only 1. Still you could get the 35. What's the ratio? 누가 빨리 계산하나? 누가 빨리 계산할까? 뭐 별거 아니지만 뭐 이런 것도 터시리 포지션과 프라이머리 포지션 간의 리액티비티 차이는 몇 배일까? 그 물었을 때 35대 65 이렇게 얘기해서 나오는 거잖아. 얼마야? 응? 4.8. So then tertiary versus secondary, which is higher? We already calculated for the primary and secondary, and it was 3.5, about 3 times. Now this is about 5 times. Okay, sounds like a tertiary is more preferred than secondary and than primary. Seems like, right? Why is it? At least it looks like since the secondary is about 3.5 times, tertiary is about 5 times more preferred. Why could be explained as the intermediate stability? Carbocation stability, you remember, tertiary was more stable than secondary and then primary, remember? What is the explanation? Why tertiary is more stable? By? 선생님 뭐라고? 뭐 답은 아는 것 같은데 좀 더 크게? 무슨 conjugation? 어? 뭐라고? 뭐라고? 이거 도와줘. Hyperconjugation. Hyperconjugation means alkyl group nearby, this CH bond here, these 2 electrons is kind of conjugating, helping this positive charges. That's a hyperconjugation. Radical is also can be same way, can be explained. Not as much as plus charges, but still, this is kind of electron poor. That's why this electron can donate partially, and it can stabilize. That's the explanation. By the hyperconjugation, radical also, tertiary is more stable than secondary than primary. Not difficult, right? So by that, the rule, this kind of the radical reaction also have a little selectivity. Okay? Tertiary is more preferred. Even though it has only one reaction site, still it could generate quite a good amount like this. Now, allylic bromination. We learned these reactions. Double bond and X2 and HX. So this one we have seen XX anti-addition, right? XX anti-addition because it forms a cyclic intermediate. Bromonium kind of positive charged cyclic intermediate and attack from behind. Okay, anti-addition. Now HX, that also we have learned. In this case, X is protonated first to generate carbocation more substrate position, and then X reacted with this position, Markov-Nikov product. Both of those reactions, is that ionic or radical? It's ionic reaction. There is no radical reactions. Okay. Now we have learned this reagent before, not deeply, but we said, I told you, the NBS, N-bromosulfonimide, this reagent is kind of a safer Br2 reagent. Br2 is a very toxic material. This material is stable. It can generate very small amount of Br2 in situ. again, and then you can build to the generator. If you add the NBS here, then similar way you could get this product here. Now, the difference here is you give light. Light is compared to heat. Light is very condensed energy and very high energy, photon energy, can break bond homolytically. In this case, in situ generated Br2 generated Br dot, and that attack this molecule. So that radical reaction we have learned, alkane and alkene. Alkane case, hydrogen was captured, and then that reacted with the halogen. So it generated a haloalkane, that was the product. Alkene, once radical is involved, it generates a polymer. Okay, two reactions we have learned. Now, difference here is now there is alkene. Previously it was alkane. The alkane or alkene, it could generate radical and then polymer, but if there is available position to the next here, that is what we call, this is an allylic position. Allyl and vinyl, we have discussed it before. This is the vinyl. This is allylic with one more methyl group. What is this? Vinyl, allyl, phenyl. One more methyl group, benzyl. Okay, this is benzyl. BN. This is the phenyl. This is the vinyl. This is the allyl. Okay. So if there is allylic position, very interestingly, this bromide radical have three positions. And some mechanism like this. Anyway, NBS is a generator of Br2. Br2 is broken. Br2 is broken by light and generated Br dot. It attacks this position. Why? And we can compare those dissociation energies. Other dissociation energy wise, it could attack this position or this position. For the polymerization, it attacked this position because there was no allylic positions. Now if you look at the dissociation energy, 465, 410, 370. This bond dissociation energy for the allylic position is lowest. That means it's easiest to break. And somehow, now we add one more here. So far, primary and secondary, tertiary stability we mentioned. Very interestingly, if there's an allylic position of a radical, that can be further stabilized. This stabilization, how can you explain? Up to here, the stabilization was explained by what? Hyperconjugation. We said it's allylic. We learned something. That's resonance. That's resonance we have learned. If it's a double bond pi electron system, and then the next position, either it's a negatively charged, positively charged, or radical, all of them can have bigger playground. It can generate this kind of resonance, and it forms either the radical at this position or this position. If you call 1, 2, 3 positions, one position or 3 positions, do you get the radical on 2 position? No. Only 1 position or 3 position. Same way for the carbocation, allylic cation, this positive charge only moves to this position, not in the center. Okay? So by this effect, this resonance effect, allylic cation is further stabilized. Now, if you have this kind of double bond, and then generate small amount of radical, and it can form allylic position radical, and it can react with the bromide. Not only this product, other product it can form too. What do you expect? This is the 3-bromo 1-octane. What could be another product? 이름 주기가 어려우면 나와서 그려도 돼. 힌트? 힌트. 누가 그려볼래? 영경이 그려볼래? 내가 이걸로 메이크업 해야 되지 않겠어? 자, 그래. Intermediate of this may be the radical of this position, right? That's allylic radical. And there is a pi bound around here. It wants to help. 그래 그러지 말고 이렇게 선과 이렇게만 그려줘. 힘줘가지고 진하게 그려. 저쪽이야. 끝만 그려도 돼. 뒤는 안 맞아도 돼. 예! 저런 프로젝트가 생기겠네. 하나 가져가세요. 왜 생기는지 알겠지? 이런 게 생기니까. Now, if you look at this allylic, which is more preferred? Interestingly, this is more preferred than this. So that means, allylic position-wise, which one may be more reactive? Let's say hindered that this position is more reactive. It can capture PL and capture like this, and it is even higher product than this one. Anyway, the key point is relative stability is not so important. Allylic case, allylic radical is formed, then it can change its position by resonance. Okay? So this is the reason why we learned about resonance forming in radical reaction. Okay? 이게 제일 복잡한 거예요. 복잡한 거까지 나왔어. So today we have learned about the alkene halide reactions. Alkene, it can react with a halogen through radical reactions. Okay. So now we are moving to the next step. Before we go to the reaction, now let's think about how to make alkene halide. Okay. Halide, industrially we could make from alkane react with a chlorine at the source, but that's also very big scale of reactions. And in the laboratory, one possible way is starting from alcohol. Alcohol is a little more naturally the friendly material. In nature, we have a lot of natural products as alcohol. Alcohol case, if you react with this alcohol, by adding HX, is that acidic or basic? HCl, it's a very acidic. Okay. If you add proton source to this alcohol, what happens? Proton goes where? OH minus. So here we have seen this case, right? We have seen this molecule today, and now if you think about OH, okay. Now if you analyze those electron distribution of this molecule, electron, this one, this is a delta, bluish or reddish? It's a bluish. This is reddish. This is a bluish. So that means Delta delta, this is a delta delta minus, right? This is attracting those electrons here. Then this position, electrophilic, nucleophilic. Same as this, electrophilic. That's also electrophilic. If you add acid, H plus may go to where? To which atom? H plus electron deficient. Go to oxygen. No choice, no other choice. It goes to oxygen, not OH. It goes to oxygen carrying one positive charges. Right? Proton has only choice if you have alcohol or water, if you have acid H plus. The only place it may go is O minus position, O delta minus position. Okay. Now this molecule, with this protonation, now there is no negative charge here. Whole molecule is positive. Okay. Still, relative value wise, if you compare this one and this one, still this is electron withdrawing. Okay, electron is still this distribution. Now you added HX, HCl. Now Cl minus, it lost the proton. Is Cl minus is kind of a nucleophile, electron rich. I remove the proton. Then situation is nucleophile, and this one electrophilic position. This whole material originally OH minus. If it's moved to this way, it generates OH minus. This is not good leaving group because this itself is a strong base. Strong base means reactive. Reactive means not stable. Okay. Originally it was not good leaving group, but now it's protonated. If it's removed, even though it takes 2 electrons, it's originally +1. It becomes at best neutral molecule, water. Water is reasonably good leaving group. Okay. Now we have alcohol. We have HX. Protonated that OH. Originally not good leaving group, but it is protonated. It becomes reasonably good leaving group. Now even though with a little weak nucleophile attack, now exactly the same position attack. Now with this Cl minus attack, this position on the same line. Now OH is here, right? Otherwise my other protons are here. Now I get chloride from behind and protonate on that oxygen. Oxygen is removed. Chloride is added. Oxygen left. This is the reaction. And that reaction, which is more preferred? Tertiary is more preferred. So concept is like that, but real mechanism is not really this attack and leaving happens together. Here, we are going to discuss the mechanism we are going to discuss next week. But in here, the key idea is this water is removed first, and then it forms carbocation intermediate. Carbocation is a planar structure. Their chloride attack and finish those reactions. So in the case, carbocation is intermediate, then we already learned tertiary carbocation is more stable than secondary carbocation and primary carbocation. That's why tertiary alcohol is the faster for the reactions. Okay. That's why with this type of reagent, tertiary hydroxyl with HCl, then protonate here, remove carbocation. What is removed? Carbocation and react with the chloride and generate alkyl halide. So this is the way we can generate haloalkanes or alkyl halide. Now this is a little more sophisticated. We will come back to this later. And even HF is usually weak acid. Still, by adding HF, H protonated here, forming carbocation, and then F minus come back and then finish this. little more sophisticated reactions. So in this case, not just a simple protonation. Alcohol react with SOCl2. Now electron distribution wise, every side electron is withdrawn, then this S is the electrophilic position or nucleophilic position. That's electrophilic position because every directions electrons are shifted. So that means this is the delta plus electrophilic position. Alcohol, usually alcohol itself is not good nucleophile. Comparing to alcohol, if you lose a proton, this is a good nucleophile. If you lose one proton, that's O minus. It's electron even rich. This one has lone pair electrons. Lone pair electron can donate, but this is not good nucleophile. But if it meets with a good electrophile, then still it can attack. Okay? In this case, the reaction happens. This lone pair electron attack this position, and on the same line, remove this. Then intermediate is this is intermediate. Now, in this case, originally OH was not good nucleophile, good leaving group. Only when it has acid added, then it becomes good leaving group. Now this whole group, still, this is withdrawing all the electrons to this direction. All the electrons to this direction, even affect this oxygen, electron withdrawing this direction. So whole group becomes quite strong electron withdrawing group. Means whole group becomes good leaving group. Now in this case, the first step to release this chloride back from behind, and then push this out. Now the product is R. 자, 한 번만 해보기에 눈에 잘 안 들을 수 있어. 이거 다음 주까지 계속 얘기할 거야. So the trick here is OH usually it's not good leaving group. We activated that OH group to make good leaving group. One example of reagent is thionyl chloride, SOCl2. 한눈에 안 들어도 돼. 계속 볼 거야. 한꺼번에 얘기하기 어려워서 조금 얘기하고 또 얘기할 거야. Another type of reagent here is PBr3 or PCl3. Mechanism is very similar. OH is not good leaving group. So we wanted to make this OH good leaving group. Then we add a very good electrophile. O attack P position. Push one bromide out. Okay? Then RO PBr2. Then all of a sudden the balance is shifted. Originally, whether this is a good leaving group or not, that was the consideration. Whether this is a good leaving group or not, this is not good leaving group. But by adding this one, this more reactive group, whole group becomes good leaving group. PBr3, if O attack P, Br2, and then one Br minus was removed. O attack P position and push this out. And this Br minus, now this whole group becomes very good leaving group, which was activated, and Br minus come back and attack here, and then push everything out. So the result is RBr. Overall reaction is ROH becomes RX. OH was changed by X. Okay. So this is how we can prepare for alkyl halide. Let's summarize what we have learned today. We are going to study the key reactions in organic chemistry. The key players are alkyl halide, because halide is quite good leaving group. That means we can use many different kind of nucleophile to replace that halide. So that's a very good industrial materials. Okay. To make alkyl halide, industrial scale wise, radical reactions we have used. Alkane with a Cl2 with a light. A little more sophisticated one, allylic bromination we have learned. Allylic position is preferred radical position. NBS was the reagent, surrogating Br2. Okay. So using that, we can introduce halogen onto the alkyl halide groups. We are going to learn the next step of replacing of alkyl halide next time. But one more reaction here is starting from alcohol and moving to alkyl halide. Now, alkyl halide, if you attack with OH minus, then what can be the product? You have alkyl halide and you add hydroxide. What is your product? You have alkyl halide, you add OH minus, attack this position, what do you get? That's this one, right? That's a reversible reaction. If you start with the alkyl halide, making alcohol is reverse reaction of this. Okay? But if you need to make alkyl halide, now starting from alcohol, originally the OH is not good leaving group. Now we activated that OH group. That specific reagents, two reagents are SOCl2 or PBr3 or PBr5, both of them works. Okay? If it is a PCl3, then your product will be chloride here. SOBr2, you will get bromide product. Okay? Just the activated group shape is SO, SOCl2. SO is the activating, PB is activating. Those are the activating group, and it activates the hydroxyl group to make it more reactive, more better leaving group. Okay? And it can react with the halide. So we learn so far here, and next time now we are going to see how this alkyl halide will react and how can it change its polarity. 조금만 더 생각을 해보자. Okay, right now this polarity, carbon and halogen, this is a bluish, this is a reddish. If you want to change it, if you want to make this carbon look the reddish, how can you do it? Right now, this is electron poor. If you want to make deposition electron rich, replace the hydrogen with metal. Okay, to make this electrophilic position electron rich, do you need to give electron or remove electron? To that carbon, do you need to give electron or remove electron? You need to give electron. Giving electron is a reduction, correct? What is reducing agent? What example do you have in mind as a reducing agent? Metal powder. Okay. If you give metal powder there, for example, let's say lithium. We already have seen lithium ammonia, right? Lithium in ammonia provide one electron, and the other lithium provide another electron. So one electron provide NH3 becomes NH2 and then lithium plus. This is reduction reaction. If you add lithium here, then to make this one positive into one minus, okay, carbocation to carbo anion, how many lithium do you need? To make 0 into minus 1, how many electrons do you need? 1. From plus 1 to minus 1, how many electrons do you need? You need 2 electrons, 2 lithium you need. So if you add the lithium here, not replace this one, replace this one. Okay, then CH3 lithium plus lithium bromide. Now let's check. Bromide originally it was a delta minus, becomes minus 1. This one plus 1. This one plus 1. This one now becomes minus 1. Now we change this polarity. Usually this polarity with the heteroatoms, all the time the carbon is electrophilic, electron poor. Only option is carbon here on the right side, everything make this carbon electron poor because this is electronegative. Only option is this side. This side is metallic side. Only metal provide electrons, means add lithium powder and it becomes lithium plus. Reduction, provide electron. Then it becomes carbo anion. Carbo anion is nucleophile. Okay? So that reaction we are going to learn next time. Okay? I can highlight good electrophile. At the same time, we can change it as a good nucleophile too. Then we have electrophile and nucleophile together. We can connect it. Okay? Organic chemistry is carbon-based chemistry, carbon-based material we study. To make a more complicated molecule, we need to make a carbon-carbon bond. Okay? That reaction, very basic key reaction is alkyl halide. One we utilize it as an electrophile. The other one, if we make nucleophile, now we can connect them. Okay? So that's the key part of these reactions. Okay, any question? 자, 이번 주 다음 주는 보통 강조한 대로 숙제 시간 기다리지 말고 열심히 복습하고 열심히 생각해서 수업 시간 자체를 잘 활용하고 있대요. 그래서 다음 주 목요일까지 이 얘기들이 계속 반복될 건데 안 헷갈리려면 나름의 체계가 들어있어야 돼요. 이걸 바탕으로 계속 같이 생각하고 한번 잘 정리를 해놓으면 나중에 잊어버리더라도 다시 찾을 수 있어요. 한번 헤매면 그냥 고통스러운 기억만 머릿속에 남아있지 아무것도 정리가 안 돼요. 이 기회를 놓치지 말고 잘 생각해요. 오케이?